Welcome everyone back from the break. Our next speaker is the first keynote speaker of the conference. So I'm glad to introduce Chris Rackauckas, who is VP of Modeling and Simulation at Julia Hub and also a research affiliate at MIT, and has been like an important person in developing the scientific machine learning ecosystem in Julia. And he will give a talk today about the software engineering of Julia's SciML ecosystem. So Chris, please, the floor is yours.
Alrighty. Thank you very much. Thanks for having me here. I'm always happy to be talking at things that are, open source communities. And so what I thought I'd talk about today is not, like there's a lot of different talks that you can always give, right? There's a lot of technical talks that I'll give on parallel computing and such. But I thought today it might be nice to take a step back from the technical part and talk a little bit more about like the engineering of, open source communities and how we do it in the Julia space, and what are some of the ways that we do that, and lessons learned and such that could be kind of transferable to other open source communities that we'd be also happy to see thrive in such a way. So I thought it's a bit higher level of a talk. If you want another one, there's other talks around that we give that are lower level, but I thought this one might be the nice fit for this conference. So. For those who don't know, what is the SciML open source organization? So we're an open source organization, one of these NUM-focused nonprofit organizations. We build Julia packages in Julia, Python, and R, mostly Julia, and it's for scientific simulation and machine learning, and scientific machine learning. And I'll talk about what the topic is in a second, just so that way we're all in the same place. But I just want to give a few stats so that way you can kind of know, we have over 100 GitHub repositories, 20,000 stars across the set of packages, but about more than 100 unique contributors monthly. So that's, when I say unique contributors, I mean 100 different people show up each month, not the same people each month, but, like at least over, 150, 200 people showing up each month doing, random things throughout the organization, with about 20 core maintainers owning different parts of the project. I'm across a lot of the project, but you have other people that like take one part of it and they say, okay, I really try to make sure Catalyst works well, and I try to make sure that the this part of the nonlinear solvers is well maintained and whatnot, right? We have about 5 to 10 summer students each year, and I'll talk about some of those interactions with different companies and different, the Julia Lab and all this, and how that all kind of works out. And I'm the BDFL of this, which is the person who's stupid enough to try to want to maintain the set of packages as a unifying source, right? So if someone is not really deep in open source development, you might use open source tools. You look at that and just go, like hundreds of packages and 150 or so maintainers showing up every month. Oh, that's not many people working on this stuff, right? But if you know a lot about open source, right? If you contribute to open source, you go like 150 people contributing to these packages. Wow. Like, how'd you do that? Right? Because if you look at a lot of other open source organizations, I think, a really nice canonical example of one is always, what happened with pandas, right? So pandas in 2017, there was a whole Twitter thread that happened about how, these companies were getting mad because there was a release that made something a bit slower. And so Wes McKinney, one of the maintainers, said, there's only 2 of us working on the project, and there's every Fortune 500 companies using this thing, like chill down, like this is all we got, right? So I think that in a lot of spaces the user to maintainer ratio in open source is really unbalanced, where you might have like 10,000 users per person who actually contributes anything to the library. But we've done really well of actually bringing a lot of people to actually be core maintainers of the project, even as we've been growing the project. And I thought it might be nice to kind of talk about that aspect of growing open source, not just in terms of users, but also like this growth of maintainers, right? But before we get into this whole thing, what is the, let's at least talk a little bit about the core topic of this software ecosystem. Like, what is the SciML open source software ecosystem even all about, right? What are we doing here? So, here's actually a picture that I stole from y'all, right? The Chapel folks on Twitter, I think, are the ones that really kind of put this out there, right? That there's this kind of benchmark. I think this is the multi-language benchmarks that's if you search on Google, you'll find one that's been maintained for many, many years. And the Chapel folks have taken this and they plotted this in terms of, how expressive it is a language, which is, what is the code size, and how fast does it run, right? So, is it slow like Python or is it fast like C, right? And you have down here in the bottom left this kind of Pareto area, that, very simple code that you can write in very high level, that runs fast. This is Julia, and also I guess Chapel, you're down here as well. We're both good friends down here, right? I think that the two languages are kind of different in some ways. With Julia being something that's dynamic, right? So it's like a language that you can run interactively with a REPL, and it uses a just-in-time compilation model. But I think that there's like some shared goals in this respect of you shouldn't have to write simple code in Python and then rewrite it in something like C or Rust just because you want performance, right? That's just one of the key ideas with Julia. Can you make the simple code that you write the first time? Maybe you might do a very small tweak, but boom, now it's as fast as the C code. You don't have to have two versions. You don't have to rewrite anything, right? Now that's the Julia, the programming language. What we do in the SciML space is we work a lot on solvers, right? So one of the solvers that we're really well known for is differential equations.jl. So we write a lot of ODE solvers where for example, I like to highlight this benchmark where you can see the performance of using something like R. Right here's R using DE-solve calling LSODA. So even if you have a solver that is fast underneath the hood because LSODA is a Fortran code, if you have an R code calling the Fortran code, ODEs is still something that can be quite slow, right? The reason for this is because there's a lot of these equation solving problems are higher level functions, right? In order to define an ODE, you define a function and you give it to the solver. But that function that you define is actually the thing that can take most of the time. And so, there's a lot of these high-level languages like, oh yeah, like we write all of our software code and, we write our underlying library in C and Fortran. So don't worry, use, R, use Python, use MATLAB. It doesn't actually apply to the scientific computing domain so well in these cases because the user code is actually a function in R. And so therefore, when you call the Fortran library, it keeps on calling R, which is slow. And so, even if you use the fast Fortran library, you lose orders of magnitude performance, right? And then you could see like, okay, MATLAB has a JIT. The JIT's not so great, but it's okay. It does its thing. Then you see like, okay, then you have like the C and Fortran libraries, and you say, oh, this is the foundation of how fast you should be. And then you see that the Julia libraries are down there, right? Which is, not just, it means it's not just something that's compute performance, right? There's a lot that we do in terms of, CPU specific, SIMD, and a lot of, refine things, but you wouldn't get this gap if with just looking at performance. This is also differences in the underlying algorithms that are used to solve, right? Newer algorithms, better time stepping techniques and things like that are used and then be able to get this gap. And this is showing, for example, one non-stiff system, and this is a system of stiff ODEs where you can see similarly that you have the R, Python, MATLAB all the way up here, and then you have the C and Fortran. You see that new methods only in Julia are really far down there, right? So people really simplify it down to like this, a lot faster than Python, MATLAB, and R, and then also beats out C and Fortran. But then the core of it is really like more about implement new methods, but make sure that they have performance, right? Make it so that way people who are frontline researchers developing the newest methods, right? Not using the methods from the 1980s, but now all the improvements 50 years later, making it so that way it's very easy for these people to get on the front lines and implementing things, but also have it be efficient because the newest algorithm with the newest code, that's actually that combination that's really going to get you there, right? And of course, we do a lot with high performance computing and parallelism. One example of this is a set of GPU compatible differential equation solvers. Different GPU compatible differential equation solvers that we put out in earlier, I guess that was in 2024 now. Where we're able to demonstrate a lot of performance gains over something like Jackson PyTorch, right? And the reason for this is actually pretty clear, because again, I want to kind of highlight the type of problem that shows up here and the way to think about different sets of problems, right? A lot of times when you're in the Python and C and MATLAB space, right, you make this assumption that everything that I'm going to do is going to be some array call into some C or Fortran library, right? You say, okay, like I write a code, the user's using Python or they're using R, but they built a big array, and then they built a big matrix, and they do a matrix multiply, and maybe there's overhead of the interpreter that's like 200 microseconds or 200 milliseconds or whatnot, but the matrix multiplication, that's in Fortran, that takes 15 seconds, so we don't worry about anything else here, right? Of course, that assumption is broken down when you're using ODEs, right? Because you have to keep on calling a function that the user writes. And so this assumption breaks down. And so this is a very good area for new programming languages and new tooling and everything to really take hold, because, the classic assumptions about array programming and vectorization just simply don't hold in this domain, right? Turns out that there's a very similar thing that happens when you get into GPU computing, right? So, when the way that the libraries for JAX and PyTorch, they go, like, we're going to build new ODE solvers, okay, and they're gonna use some new algorithms that we have from the differential equation space, okay, they're on the right track. So how do we get like 100 times faster than them when JAX and PyTorch, right? It has Google money, it has Meta money, right? How do you beat that, right? And the key thing is that a lot of the machine learning libraries, they develop in a way where they're based off of array primitives, right? So basically, you have an array on your GPU, and you have a matrix on the GPU, and you do matrix vector multiplication, and that calls a kernel on the GPU, right? And so this problem that we looked at was, if you want to parallelize ODE solves on GPUs, and you want to do this over ensembles of many runs of the same ODE over different parameters, the way that they would do that in the machine learning type libraries is they would, instead of solving an ODE, let's say you have 3 terms for your ODE, if you want to solve it n times with different parameters, you would make your initial condition vector be, that 3 values, but times n, right? So you get a really big array with multiple copies of your ODE, and then you'd have, instead of your 3 parameters, you'd have, 3 times n parameters, and you would call your function in a way that you're saying, I VMAP over it, or you effectively, use array operations where anywhere that you would have had a scalar operation, which is doing the same operation over all ODEs, right? So it's transforming solving one ODE at a time into solving n ODEs at a time using array operations. And if what you have is an array accelerator, like a machine learning library, that's the way to parallelize an ODE solve. But what we're able to show is that not only is there a CUDA-based ODEs, CUDA-based solutions for solving these kinds of ODEs in parallel, but then we built one in Julia as well that was instead saying, okay, let's take the entire ODE solver and generate kernels for it, right? Generate .ptx kernels, so that way the actual kernel that's called is solve the entire ODE with this initial condition, this parameters, rather than being every single step of the ODE, right? So, instead of taking an ODE function and saying, if this would have been a scalar plus a scalar, turn this into, the scalar of every ODE plus a scalar of every ODE, and do that for every single operation side of the ODE, right? Instead of taking that approach to the machine learning libraries, we said, let's take the entire ODE solve, turn it into a kernel, and then call that kernel with E0 and P. And that difference in the way that you parallelize is then about 100 times, right? Which should make sense. I think that folks here who do a lot of parallel computing, you probably just go, yeah, you wouldn't turn a big MPI program into, hey, I'm going to do a matrix vector multiplication as one, so do all the communication. Now do the next thing with communication. Now you try to do as much as you can and try to minimize your communication, right? That's effectively what's going on here. With the interesting thing being that with the Julia is able to natively compile to the GPUs, right? So we can take what exactly the same code here that's the fast differential equation solvers, but now turn them into GPU kernels, and this gives us the things that are much faster than the way that the machine learning libraries could, because of kernel building. But then our kernel building compiler can also compile to CUDA, it can compile to Intel's One API GPUs, it can compile to AMD GPUs, and also compiles to use the Apple Metal GPUs, right? So we do a lot of this kind of parallel computing in this form, and you might immediately see maybe a difference in the way that we think about this this way of building tooling where, I mean, I basically just said, hey, we have a tooling that is doing this kernel generation, and we have an ODE solver, and this is what happens when you put them together. I'll talk a lot more about that, right? Like how we can kind of get these features as things that just kind of exist through combinations of features. But that's kind of like an idea of what we do with the SciML space. We build a lot of these solvers, we make them fast, and then there's this other piece that I'll mention in a second here. But we do this in things like linear solving, nonlinear solving, differential equations, integrals, optimization, and all these kinds of problems. Now, where the name SciML comes from is that it's not just a library for fast solvers. I mean, it is a set of fast solvers, but it adds a little bit more to it. So what we really add to this space as well is the fact that we try to do a lot of this thing known as scientific machine learning, where the idea behind it is, if you want to make a very good prediction, like let's say you want to be able to make a prediction from a time series, right? One way that you can do this is you could take a large data set, right? You can say, okay, I have a huge data set. You can do some machine learning, and it learns how to make predictions from your data set, and boom, as long as you have enough data, you get a good prediction, right? The other way you could do this is you can have an informative scientific model, right? So you have some model of, say, how the chemical reactions are involved, or you have a model of, the equations of general relativity, right? Then you can write that down and say, okay, if here's where I'm at, then there's where I will be in the future, right? But, in order to, what we do a lot with is this idea of, if you didn't have very much data and you still want to make a good prediction, could you compensate for your not so much data by bringing in some element of mathematical models, even if you don't have a full model, right? Like Newton, could you if you didn't know general relativity, could you use Newton's laws, knowing that they're incorrect, with a bit of data, and figure out, like, okay, here's how I correct my data predictions using Newton's laws, and could that actually just be something that's better, right? So a lot of the SciML organization is around building scientific simulators, so that way they can connect to these machine learning and data spaces for doing this kind of research and doing these kinds of algorithms. I want to highlight one particular kind of algorithm that we do here. This is the universal approximator differential equations, also known as the just universal differential equations, where what you do is you build a model with everything that you know. So you say, I know that if I leave rabbits in a room alone, I get exponential growth in the number of rabbits. So x equals alpha x, where alpha is positive. And if I leave, wolves in a room together, then they all seem to start dying out. So, y prime equals minus, theta y, right? I know this. I know these. But what I don't know is if I put rabbits and wolves in a room together, my mother really never told me what happens when they're sitting in the same room for a few days. So there's some unknown relationship, which is how does X and Y interact, right? And so what you might want to do is you can say, well, I might have a little bit of data, but with just this little bit of data, it can be really hard to predict the future. But what I could do is I could say, I know that rabbits alone give exponential growth. I know that wolves alone give exponential growth. I don't know what happens when you piece them together. From this data, can you complete the model for me? And then try to extrapolate once you've completed the model. And what we find is that this approach where you kind of do this model discovery, right, where you learn what terms are missing, and you use that to be able to complete the model. We find that this gives you, orders of magnitude better predictions than just purely data approaches alone, and much better predictions, of course, than just using the little piece of the model that we know alone, right? So it's this kind of machine learning that is guided and integrated with the scientific equations. And this is all done, the way that this is done, it has to have some kind of training process, which requires the ability to be able to automatic differentiation of the model simulation software, which then comes down to the idea of, can we make it so that way our linear solvers, nonlinear solvers, differential equation solvers, integral solvers, and optimizers all are able to compute robust derivatives as well, right? If you're curious about the topic of why I say the robust derivatives, I give a talk called The Numerical Analysis of Scientific Machine Learning. It's on YouTube, and it goes into the fact that if you go to, for example, the PyTorch or the JAX differential equation solver libraries, we're able to show you very simple linear ODEs where they compute the wrong derivative. In fact, their techniques don't even converge to the correct derivative. And you can show that, it has to do with characteristics about non-reversibility of ODEs, and that automatic differentiation is not necessarily a convergent algorithm. So actually getting things to converge to the correct value, right, is a very deep numerical analysis thing that you really have to look into a lot of the details in order to make sure that, just like how you can't just like write down an explicit Rackauckas method, just go, yeah, I'm done with ODEs now, everything's done, right? Even though mathematically Rackauckas method is always convergent, and in practice, many times it's unstable, right? And there's a very similar thing that happens with the training processes and the derivative calculations. And so there's a lot of what we do in the technical sense where we talk a lot about computing the gradients accurately and fast, right? And so what tends to happen then, like one of these things that you'll see from the SciML community is something like this, this what I'm showing here, which is the accurate extrapolation from the knowledge that we know. Where here what I'm showing you is this case where you have a binary black hole system, so there's two black holes moving around each other. It's a two-body problem, but black holes are rather large, right? So you can't really just assume Newtonian mechanics. You need general relativity, but let's just assume Newtonian mechanics, right? Let's just assume Newtonian mechanics in the rotating frame of one of the black hole systems, and then we just have to assume that okay, there's something wrong about our dynamics. We know Newtonian mechanics, but there's some corrector. This corrector is a neural network F1, 2, 3, 4, and let's learn how the system would need to be corrected from some small amount of data, right? So let's basically take Newtonian physics in a case that is not well described by classical Newtonian physics and learn what the relativist correction should be. And this is then something where if you want to kind of get a feel for what we do, you can go to docs.sciml.ai. If you go to docs.sciml.ai, you'll see the showcase of cool examples. You'll find this discovering relativistic corrections to binary black hole dynamics. And you'll see that this tutorial is fully written out for if anyone wants to run it on their own, where you can see you start from a prediction of Newtonian mechanics, where you have a two-body problem, which is going in a circle, and it learns from a small amount of data how to do the perturbation, which then gives you this Lysygy pattern, which is one of the ways that we first confirmed general relativity was the Lysygy pattern from the perihedron of Mercury, right? And so it shows you that the dynamics is substantially different, and has learned something that has the characteristics of general relativity, right? So this is the kind of stuff that you'll see inside of the SciML ecosystem, right? So it's a lot of solvers, but the solvers connecting, connecting with high performance computing, GPUs, making sure that the algorithms are fast, but then also making sure they're all compatible with automatic differentiation, compatible with the machine learning libraries, and then putting this all together in one cohesive whole to be able to do applications like this, where you can write down, oh, here's everything I know about my biological system, but here's the data that I have. Please autocomplete for me. What chemical reaction did I not know about that was required in order for this data to occur, right? So that's what we do as a SciML organization, and of course that could be its own whole deep story about every single algorithm in there. Go see the other videos if you care about that stuff. What I want to do with this, I want to talk about open source communities, and I want to talk about, again, how have we been able to develop this software from the community that we have, how we've been able to get so many contributors. And then one interesting thing about the way that we develop the scientific machine learning libraries is the composability model, right? And the reason why I want to highlight the composability model is that, again, like not many other ecosystems do it this way. If you look at, for example, something like PyTorch, right? PyTorch is a library. Yeah, it has, some distributed computing. It has some, GPU computing. It has ODE solvers, right? There's someone who built an ODE solver library on there, but but it has its own JIT compiler. If you actually start to look at what PyTorch actually has, it's almost its own library. It's almost its own language, right? And then if you look at, like JAX, it's basically its own language, right? When you say, hey, I'm going to go to SciPy, when you go to, or when hey, I'm going to use Python, I'm going to solve an ODE, 99.9% of people think you're going to use SciPy's ODE solver. And 99.9% of people will use SciPy's ODE solver because it's more battle tested, more robust. It's actually a lot more faster than a lot of the other ones in most of these cases. So SciPy as the ODE solver, it's like the ODE solver for Python. But then when you tell someone like, oh, I'm gonna now use, PyTorch because I need to do the machine learning part with this, right? Because I want to mix machine learning and I want to with ODEs. Suddenly just go, well, I can't actually use SciPy. So we have these different ODE solvers in PyTorch, which then, it doesn't have all the algorithms of SciPy. They're working on rebuilding some of it, but some things are different. And then you go, well, there's also the machine learning library in Python, which is JAX. So they have their own machine learning library that has its own things though. And then they go, okay, well, what about making this one GPU? Well, if you make you make the PyTorch one GPU compatible, you don't the work on making the JAX one GPU compatible is different, and the SciPy one's still not GPU compatible, and And so when you try to say like what is the ODE solver of Python and how should I connect that to the machine learning library, you get this answer that is, well, it depends. Every machine learning library, everything you want to do, you rewrite a new solver, I guess, from scratch. You can rebuild things, right? But in what you see here from the Julia open source ecosystem is we just say, like, oh, what I want to do machine learning with my differential equation solving. What should I use? And it just goes, okay, you use the differential equation solver, right? This is the differential equation you always use. Why would you use anything different, right? Oh, but I want to do that with machine learning. Oh, use the machine learning library. You use the automatic differentiation and Lux. Why would you use anything different? It's like, okay, like, there is no different library. And so you can instantly see how that would just grow your contributor base instantly, because instead of having 5, 6, 7, 8 versions of these solvers being rewritten every single time you want to go to a new library, every single time you want to say, okay, I want to support CUDA, right? You have one ODE solver library for CUDA, one ODE solver library that's, kind of built out for AMD GPU, and you have one weird guy who's living in France who just decided to build one for one API and then discontinued it 2 years ago, right? Like all that whole thing in the ecosystem, we just say, no. We have one ODE solver that is also the thing that works on all GPUs, that is also the thing that works on all machine learning, that is also the thing that is compatible with HPC. We just got one thing that we just keep on working on, and this is why we can get so many contributors, right? And the question then is like, how do we achieve that, right? What is the technical way to achieve that? Because of course that's kind of like a lofty goal, but how do you do that, right? So the way that we do that is kind of one thing is that we build with a lot of modularity, where we say, okay, we have all these different pieces, but instead of trying to solve every problem inside of one monolith of a repository, right, we have many different smaller pieces that we chop things into, right? So when we say we have SciML, right, we say, okay, SciML has a simulation portion which has differential equations.jl. Well, there's also diffeq GPU, which is a sub-library that just takes differential equation solvers and pieces them together with the GPUs, which can take any of the differential equation solvers. And each of the differential equation solvers are sub-libraries for things for SDEs versus delay differential equations for ODEs. So if you just want to just work on one topic, right? Let's say you're just like interested in the research of SDEs, you can just go straight to stochastic diffeq and ignore that anything else exists. But but then the same solvers, they also connect to inverse problems where you can use, it connects to Turing, it connects to automatic differentiation and enzyme. So you can, for example, build a brand new SDE solver into stochastic diffeq, and by the transitive property of how things are connected, your solver, the moment it's done, is compatible with enzyme reverse mode automatic differentiation with specialized adjoints that have this provable, convergence properties, and so yada yada yada. Now suddenly your new SDE solver can be used with machine learning, even though you didn't have to connect any of those bridges, right? And so it's kind of developed in such a way where it's not necessarily a monolith. There's all these little pieces, but all these little pieces really connect together, where you say, okay, this piece does this over here, this piece does this over here, but the same automatic differentiation library is in the optimization tools, and you use that inside of the Jacobians of the differential equation solvers, and you reuse the differential equation solvers in the global sensitivity analysis, and everything just seems to have this web of reuse around, right? So and one of the things that people kind of see when they come to the Julia SciML ecosystem, they go, oh, like this SDE solver has 400 dependencies. And it's like, yeah, it's got this web of things where we reuse a lot and we work a lot with other people who are not in our organization. So that way they're part of this development process. And one of the ways that we really do this is through making sure that we can develop things using generic programming through multiple dispatch, right? So here's an example of, here's an example of doing this, right? Where I'm showing you that you can define this struct and you can have this array of planets, right? So here, for example, I have an array of planets, and then it's an array of structs, but I can solve this on CPU, but then I can also move this over to GPU because you have this CUDA.jl library that endows that we can take anything that has a bit structure, like a known bit structure, and turn it into something that works on GPUs. This structure right here knows that there's a float 64 and two float 64, so it knows exactly how many bits, it knows the whole type thing. So even though we're a high level language, right, we can use the CUDA compilation that is a part of LLVM to be able to generate new kernels and new functions for GPU that are specific to this planet structure, right? And so because of this, we can say like, oh, anything anything that operates on arrays is compatible with GPUs. Or there's no special torch array that works with GPUs. This is just a standard Julia array. I could convert into a Q array, and now anything that works on Q arrays and Julia arrays, it works inside of my system, right? And the differential equation solver just says, all I need to know in order to work is I need to know how to be able to compute, map operations or broadcast operations, and I need to be able to compute norms. Anything else that happens is inside of your F function. So it can take this array of planets or it could take this array of planets. It doesn't really care. And so arrays of planets, Q arrays of planets, every single weird array type you can think of becomes ways to be able to give inputs into the ODE solver, which means that if someone comes up with a Q array, boom, the ODE solver that works on Q arrays is differential equations.jl. Someone comes up with an AMD array for putting something on AMD GPUs, and boom, if they put it into the differential equation solver, then differential equations.jl is the ODE solver for AMD GPUs. And similarly, basically, this kind of generic programming approach then makes it so that way the same solvers just can work as long as it works on arbitrary array types. And then you can start to go even further. You would say, okay, not only do I have arbitrary array types, but I also have all sorts of number types, right? So, so here this is showing that I can put units inside of the planets, and then I can do the same operations on CPU, and the units will even work on GPU, right? Because this is property of Julia, this multiple dispatch, that it's able to change what plus means, it changes what multiply means, and so suddenly calculating the total energy on float 64s can be something that is calculating the total energy on unit full numbers, and then if you stick it inside of a CUDA vector, it's going to need to JIT compile new kernels for this new number type, right? Because this number type didn't exist before, but it'll JIT compile all these kernels, and suddenly your code will also, with all the units, will run on GPU, right? And again, you making something where you have arrays, Q arrays of unit full numbers of float 32, you take that whole type and you just say, well, as long as it acts like numbers, and as long as these things act like vectors, then I could stick them inside of the generic ODE solver, and now I can solve ODEs on this thing as well, right? So then suddenly someone can just say, hey, look, I want to implement unit systems by working on a number type, and someone else says, hey, I want to implement Intel One API by working on an array type that will then run things on this GPU. And then also, be able to compile Julia code to kernels for this, right? When you stick those two things together and then you stick them inside of the ODE solver, then you get a unitful, ODE solver that runs on Intel GPUs. It's just this composition of features that comes along. And I showed cases here on, so here's, for example, a very simple example where it's just a pendulum, right? So here's a pendulum, you define the ODE, you give it some, here's my parameters, define an ODE problem, you solve it, you use an automatic solver selection, and it plots it with a nice continuous lines, right? This is what we show as like a very simple, like introduction to your ODE solver kind of example. But now what I do is I just say, okay, I want to do this in a way where I have uncertainty quantification, right? Where, Monte Carlo measurements defines a number type that does uncertainty quantification at each step, right? So, it does plus, but in a way that pushes forward distributions. It does multiply. It does, sine, all these operations, but pushing forward distributions instead of floating point numbers. All that you do, if you notice a change here, all that you do is you just change your initial condition and parameters from being something that is a 64-bit floating point number to something that is then a number with uncertainties, right, defined by Monte Carlo measurements. You take this new number type and then you stick it inside the ODE solver, and boom, this is what you get as the output, right? The ODE solver just solves on this new space. And so, like I think that when this is very different from when you look at a lot of other ecosystems, right? Like for example in C++, there's like this MUX library, right? That's done by Sandia, where again they write it is for uncertainty quantification, and they write down like, okay, here's all the things you can do with uncertainty quantification, right? Like here's all the routines that we have. Right. This is instead of trying to build it and say, hey, look, Monte Carlo measurements is a library for uncertainty quantification, and we support uncertainty quantification for, we have an uncertainty quantifying Newton's method, an uncertainty quantifying ODE solver, It says, I have a number type, and if you take this number type and you stick it into the ODE solver that you already know how to use, right? Because this is the standard ODE solver in the language, then you get uncertainty quantification, right? Just add my piece to this other thing, and we'll compose it together, and boom, now we work together. And this level of composability then makes it so that way you can when I count the contributors, I'm not even counting all these people that are building these extensions that just kind of work together through this composability, and it much more centralizes your ecosystem then, right? Because then people can say, I want to work on this ODE solver because it's the one I use when I use GPUs. I want to work on this ODE solver because it's the one that I use when I work with machine learning. I want to work on this ODE solver because it's the one that I use when I use uncertainty quantification, right? Instead of having these little silos of different versions of doing solving, right? You have one centralized piece that's connecting with all these different applications. And so one thing I like to show too is like you think about for example, probabilistic programming, right? Doing Bayesian inference, right? If you go to something like Stan, right? If you go to like the standard, I think the most used probabilistic programming language, right? They have differential equation solvers that are built in there. Now there's not very many because it was done as a Google Summer of Code project in like 2017, and the guy graduated, and so it's not maintained all the time. There's some questions that'll be like, oh, when will you support SDs? And it's like, we won't get there and everything, right? It's like, and also Stan tends to be used from R most of the time. And you're like, okay, but the Stan ODE syntax is very different from the RDE solve syntax, right? So there's all these kind of issues that happen in this probabilistic programming space because the people who do probabilistic programming needed to also implement any differential equation features that they wanted to be able to put into Stan, right? Whereas when we look at the Julia ecosystem, you say, okay, you have Turing, you have that does Bayesian inference, you have differential equations.jl that solves differential equations, and if you want to do Bayesian inference in differential equations, you just piece the two libraries together, right? And I can just go to the tutorial and show you exactly what this looks like, right? If I go to turing.ml, I go to tutorials, and I go to the Bayesian differential equations, right? What you'll see is it just says using the Bayesian inference library, using the differential equations library, and I define a differential equation. Again, this is exactly like what I showed in all the other examples. And then I stick this same solve command right inside of the Turing model, and boom, now what solver is it using? Well, it's using the solvers of the solver library you already knew, right? So instead of it being its own world of hey, let's try to get enough differential equation solvers inside of Turing, right? We just make sure the libraries work together, and now we tend to work together quite often because hey, look, all the Bayesian examples that I show, all they're being done in combination with a library where we can work independently but together, right? And so you can have code that is then truly generic, right? So the things that you can do, for example, through number types is, of course, you can make different float 32 versus float 64. But you can also pass through uncertainty. Things like symbolic computing, right? Like SymPy implements things that are effectively numbers, like they have number operations. But I mean, if you can make it so that way you have this composability, one nice example like the show is that with the symbolics.jl, if you stick symbolics.jl operations into the ODE solver, right, with a fixed time step, you can actually generate the symbolic representation of that time step and use that to be able to do, say, write down the optimization problem for optimal control, right? Because you want to be able to, write down a collocation and be able to Well, you don't have to implement any collocations yourself, right? Because the ODE solver already exists. Just put symbolic elements into the ODE solver. It'll spit out the symbolic representation of a step of the ODE solve. There you go. There's your collocation method, right? Like stop. You don't need Casati, to exist, or you don't need the optimal control library to exist. You just generate it from the symbolic computing with your ODE solver, and generates it in just a few microseconds. So why are we rebuilding things, right? Another thing that comes also from this genericness is automatic differentiation, right? So instead of saying I have a torch array, which is and torch array is a thing I know how to differentiate. So write libraries that work on torch arrays, and you want to be able to automatically differentiate your ODE solver, or write a new ODE solver that works on torch arrays, so that way you can do the differentiation via torch arrays, right? Instead, we just say, our ODE solver is this generic piece. And for example, forward_diff.jl, which is an automatic differentiation library that works by changing your input numbers into dual numbers, sliding it through your program. And just like how you slide the uncertainty propagation through this program, you slide dual numbers through the program. Boom. Okay, the same ODE solver is now the one that's compatible with forward mode. Now you make it also compatible with reverse mode, right? And so now there's really it really centers the ecosystem then, because all this idea of I want to rewrite it for this use case suddenly just becomes no, just change the input. It's like 3 lines of code, and we got this, right? And I think, and this really kind of was highlighted. So there's a scientific computing cheat sheet, the scientific modeling cheat sheet that I put out a little bit ago, which had comparisons between MATLAB, Python, and Julia. And one of the difficulties I actually had when writing it, let me see scientific. Let me see how easy it is to find. So cheat sheet. Scientific modeling. I can probably find it after my talk. Oh, it's going to be right here. Yeah. So you can see, it has all these pieces. But the difficulty that I had with actually kind of writing this was the non-composability of some ecosystems like Python made it so that it was rather difficult to even express. So for example, right, okay, if you're solving differential equations inside of Python, you probably use solve IVP from SciPy. Of course, that's what every course notes would tell you to do. And then the moment you go to DAEs, it's like, but this doesn't have DAEs. But you could go to the Asumolo library, which requires you build some stuff from scratch. So you need to know how to, run make and everything. But you could go there, right, if you want DAEs, and then, and then the other thing is, but most of the operations you want to do with SciPy, right? And then you go to optimization and just say, you go to optimization. If you use SciPy as your optimizer, you can't run this with PyTorch AutoDiff. And if you want to use Casati, because Casati is what you use for optimization, optimal control, you make sure that you don't follow this optimization section, because it has its own optimizers, right? And so I think when just trying to teach someone how to use the language, it just naturally shows itself as in the way, right? Or you just say, SymPy is a thing that's mostly used in Python for symbolic computing, but Casati, which is something that's used in modeling, also it has a different symbolic representation. They're incompatible. So if you want to do modeling, you use Casati. If you want to, do a symbolic simplification, use SymPy, right? And but also don't try to put SymPy operations into a PyTorch tensor. These cannot, so you end up with every single section being like, okay, for this section use PyTorch. For this section use SymPy, but it's not going to be compatible with the other section. For this section, and you can see one of these show up with every single one. And I think that, again, this was not even trying to showcase anything about the libraries. This is just trying to teach someone how to use it. And it's just so apparent when you're trying to teach someone, is hey, just be careful about this, be careful about this, be careful about this. None of the libraries work together, right? It's just a nice thing to kind of just show you what the meaning of this composability is, right? Because Casati, if you know SymPy and you don't know what Casati is, right? Casati is this library that does representations of differential algebraic equations, be able to do dynamic optimization on them. And then you might ask, what if you want to simplify the system? Well, you can simplify symbolic systems in Python, right? You can do that with SymPy, right? SymPy has all this kind of stuff for simplifying systems. But how you build a model in Python is with Casati, and Casati doesn't have the simplification stuff, right? And so you end up with this, like, so then you have one team that's building out simplifiers in Casati right now. We have another team that's building out new ODE functionality in SymPy, and you go, well, the Python ecosystem has, twice as many developers as the Julia ecosystem. How will you ever keep up? You say, well, they're just writing the same thing 10 times. So I think if you count it correctly, we have like 5 times as many people building things, right? And so it's like a funny little thing that happens because of composability, right? And so that's one story to talk about. And the rest of the time here, I want to kind of discuss then the growth model that we've had, right? Which is another, I guess, even more kind of semi-non-technical kind of discussion of what does it mean, and how do you actually build out an open source community, right? So, Julia started in 2012, though it didn't really exist until 2018. I mean, I didn't join the community until 2016, and 2017 was my first JuliaCon. So, I think 2018 is when Julia 1.0 came out. And so you kind of have this, like, there be dragons before that, where some nerds would poke around and whatnot, but it really came into existence in 2018, right? One of the interesting things that you'll see about this kind of Julia space, of which I was kind of involved with, is that you had some companies that were developed around trying to improve the open source community while having a commercial model with it, right? And I kind of want to describe a little bit of that as well, because it's really shaped a lot of the maturing of our ecosystem. Right, so even though it started in 2012, Julia Computing was started in 2016. Pumas AI, a company, was started in 2018. And then you have like Julia Hub. We had our Series A in 2021, and then all of these really kind of ballooned into being a very large set of the open source maintainers. I mean, it's not everything, right? I think that, for example, if you look at the core compiler group, about 1/3 are at Julia Hub, 2/3 are at various academic institutions around, or other other industrial communities. But I think that there's something to point out here, that the Julia community has had a whole lot of contributors. It is very difficult to keep a lot of contributors to be mostly full-time in the ecosystem. And so how do we do that? Well, one of the ways that we've done that is through a certain growth model. So one of the things that I'm associated with, right, one of my hats is Julia Hub, or at MIT, in the MIT Julia Lab, where it's a academic lab. It's a rather large academic lab. We generally have had around 16 to 20 students at a time. If you go to julialab.mit.edu, you'll see all the different research that we do. But the key thing is that this is an academic lab where we really focus on do new algorithms, but not only do new algorithms, but benchmark them well. And by virtue of benchmarking them well, you kind of have to write good software. And so do this in a way where you're creating software and adding it to the system. So actually, a very common thing for someone to do, right? And you can kind of see through this kind of way that we have this composability. One PhD thesis, right, is usually like, you always kind of make the joke of like, okay, here's everything that's known, and you make your small little contribution, and boom, like that's your whole PhD, just figuring out how to make your contribution to the whole space, right? You can see that we kind of developed this in such a way where, yeah, your small contribution of, a new algorithm that can do some kind of cool thing on ODEs, or a new ODE solver, can be slotted in as just a small extension inside of this space. And so because of that, you can be doing completely novel research while working on an open source library, and be contributing to this whole ecosystem that's out there. And so what we care about a lot with our PhD students is not only that they have some publishable work, but they're actually contributing to the open source ecosystem in this manner. So you'll find that like a lot of maintainers and creators of a lot of these scientific packages have actually come through the MIT Julia Lab, right? Not everyone ends up being an open source maintainer. I think it ends up requiring a certain kind of tenacity to be able to wake up every morning to 50 new issues of, oh, did this turn out slower than and I found this weird bug that happens if I take your new solver and I put it on, this random astrophysical model or whatnot. You just go, maybe I don't care about astrophysics, but let me dive into this bug, right? Very few people end up becoming, truly open source maintainers, but I think that we have a very good ratio where we've had, like 15 to or 20 folks, over a span of just like the last, 7 years that really kind of become embedded and really major players within the Julia ecosystem by taking this approach where we say, okay, your research is not something where you can just write a throwaway script, but implement your new method as something inside of the package and benchmark it. And you'll have better benchmarks too, because you don't have to say, oh, when someone creates a real version of this, no, this is the real version, benchmark against the real things and show someone that it's the best problem in practice on a real problem, right? And so we've had many people from the Julia Lab become open source maintainers through this kind of push. But again, like even though we've done a lot of this, right? There's a lot of issues with relying on a purely academic ecosystem as the way to maintain open source. I mean, especially in the United States in the last year, right? For various reasons, right? Trying to make sure that you can maintain a large lab, all based off of consistent NSF and NIH funding is just not conducive to having a maintainer base that is strong over decades or more, right? Not only, I mean, there's a lot of things to point out here. One of them is that, if all the grant funding, if all the academic funding is grant funding, university overhead takes more than 50%. So you have to get, twice as much money that you think you're going to need. And then after, the funding's not guaranteed after that. And the worst thing is that the moment the student actually becomes useful, right? The first 3 years are kind of, trying to learn what they're doing. They're taking courses half the time. So you have to tell them, yeah, it's okay if you didn't get much research done. You're taking courses. I understand that. The 4th year, they start getting to understand things. 5th year, oh, they're really productive. 6th year, they're gone because they graduated, right? So they're like really a maintainer for like, a year or two. And then only if they land a postdoc that, like, oh, this postdoc, this lab over here, we know that they'll continue open source. Only if they land that postdoc will they continue to do the maintenance. And then only if they land a good academic position that will they continue to do maintenance. If they get sucked up into the Google machine, they might not have the IP rights to ever contribute again, right? So there's this issue with maintaining open source that happens with academic. Now, I love the academic space. That's why I still work in it a lot of the time. There's still a lot of new contributors come up through the system. But what we found was that after this training occurred, right, if someone actually wants to work in open source, how do you allow them to continue to working in open source, right? Because they want to have a paid job at that point. They can't just go jobless because they're like, oh, I love open source, right? I know that some folks who would show up to an open source conference, you're like, yeah, you know what, I do that. I live on the beach, go to McDonald's for the Wi-Fi and hack away, and then sleep on the beach again, right? But most people want to have something beyond just the open source life, right? So how do you actually put that together, right? So what we've done is we've actually been able to build out some companies where their products are built on the open source space in a way that kind of contributes back to the open source. So I mentioned this one, that's Pumas AI, right? Without going into the whole story, what Pumas does is it does this thing called nonlinear mixed effects models, where you're given some covariates, right? So this is things like weight and sex and whether you metabolize drugs fast, so like six features about a person. And what you do is then this goes into a structural model that predicts these parameters, and these parameters are then the parameters of a differential equation that then tell you how fast the drug is being emitted from your body, how fast you're responding to the drug, and then ultimately would then be able to tell you things like, given male versus female, should we be dosing the two sexes the same, or should we use different dosing based off of these characteristics, or should we be doing different dosing based off of weight, right? For one weight class, is the dose going to be toxic? There's too much, versus another weight class, is it not going to be efficacious, right? There's too little of the drug, right? And so the problem that Pumas really focuses on is this nonlinear mixed effects model, where you have this structured ODE where you then want to find out this eta and theta, these terms with respect to some condition on parameters. You're basically trying to find out the theta as being the average difference due to weight, to then be able to find out whether you could predict beforehand for a clinical trial how you should be doing doses differently. So every dose model that you've ever seen is done through this kind of measure. And so what the Pumas really did was it said, okay, we work on ODEs a lot in SciML, right? So this, and in fact, not only do we work on ODEs, we work on inverse problems of ODEs and automatic differentiation. This is something that uses all of that, but now puts it into production in the pharmacometric space. So that way, pill bottles are actually written using this software, where we can get these we can sell licenses to these companies. So then the same people working on this these open source solvers, right? You can say, hey, do you want your day job to be making these open source solvers better for pharmacometrics? We can get you a day job, right? This is effectively what Pumas AI is, and it's been successful enough so that way it was actually the go-to tool for things like the Moderna vaccine for COVID-19, right? And so the business was built out around that same exact time, and it really became the go-to because of the speed and performance at which it could give back answers, right? Because during that time, right, there was a very strong push to get the analysis done, get the FDA approval, and this is the tool that was used for the quick FDA approval. Now, why is this a space that has worked out for this? Well, what we found out was that, specifically in the pharmaceutical domain, there's a lot of folks that kind of told us like, hey, we can't use your open source software unless you pay for FDA validation, and that takes like $2.5 million. So just use your open source funds to do the validation. We'll be happy to use it in the real world. And then we just go, well, could you donate? And they say, oh, we can't actually donate to an open source project because our company doesn't have a way to be able to do open source donations. But they're a billion-dollar pharmaceutical company, so they have a way to be able to pay for software, right? They just don't have a way to be able to donate. So you put a company in front of it, and we just say, okay, would you want to pay for the software? And suddenly you get million-dollar licenses, right? And that then funds the people to work on the open source. So you can see that there's a lot of people in the open source community of Julia that are actually, again, like when I mentioned this Bayesian statistics library, the main maintainers of the Bayesian statistics library, one of them is actually there at Pumas AI, and that's where a lot of this all kind of starts to come together. Again, Julia Hub is in another one in this space, and now we're building out something in the system simulation space. So this idea of, you can do graphical user interface. So you can do this graphical user interface where you build up a model in a graphics domain, and it then is able to run and be able to generate code for embedded devices, right? You might know things like Modelica, AIMSTIM, Simulink in this space of system modeling languages. We're doing that built on Julia, and then this is able to maintain a lot of the Julia open source community around this differential algebraic equation space. You can actually see that it's being used in some cases. So our logo's on the car, and there's George Russell, right, one of the Formula One drivers, because we've worked very closely in this domain, right? And so this is showing that how, like taking this idea and then saying, hey, let's build structures to be able to maintain not just software, but also the people who contribute to the software, and making sure we can build out that ecosystem has really been helpful for our growth. So in conclusion here, right, yeah, Julia might not have the most users. I mean, Julia, it's a different list. Show it as like 22 on the ranking. So it's not bad, but it's not the number of people that are using Python, right? But if you look at who's actually contributing to libraries, you find that our libraries tend to actually have more contributors, right? And a lot of this happens because, it's a high level language. So it's if you use Julia, you can develop the library. So it's very easy to make that transition. But also the modular design means that there's there are these focuses of the ecosystem where you have one differential equation solver that everyone is then trying to make sure it's compatible with the rest of the world. And so you centralize this development. And then we've also been able to build up a lot of these research organizations in such a way that they can further open source. So yeah, I mean, Julia is not the biggest language right now. Python has more users, but with this focus really on making sure that we can have a good developer experience, and having lots of people contributing and maintaining these libraries, let's see how this works out a decade from now. I kind of think that this approach will at least lead to very good software. So thank you very much.
Thank you very much for your talk, Chris. Please join me in thanking the speaker with a virtual round of applause. So now we have some time for some questions. Are there any questions from the audience?
I've got a question.
Yeah, go ahead.
So you talked about how one of the ways that you're growing the various set of methods available to Julia libraries is by having PhD students not only like develop methods, but also write software that gets contributed back to Julia. I'm curious, one concern that I would have with this is, as you mentioned, like not every student eventually becomes an open source maintainer. So does this not increase the kind of area of code that you have to maintain and keep working with time? And how do you deal with those challenges?
Yeah, it does. It does. I mean, that is a downside of it, right? Where, you might have a student that comes in that just says, I'm very into Rada methods, right? They're there for 3 years. You have the Rada methods, and then they take off, right? And you go, okay, well, now it's up to everyone else to have to help maintain this, right? Yeah, that is something where you have to deal with that maintenance burden. We do make sure that everything is developed, and we enforce that all these students have to do things in a very structured way, where they have to have a lot of CI testing. They have to have a lot of the CI testing isn't just testing of correctness, but also has to be performance, right? Compatibility with GPUs and everything, right? It's really got to cover the space. And then it has to have if you have a large set of testing, then at least it's very clear when anything breaks. And then one of the other things that we found actually helpful within the last year as well is that if the entire ecosystem is also forced to document every breaking change that goes on, bringing in LLMs to be able to say, hey, look, there's now a breaking change over here, change the names, or change the syntax that's required, so that way this piece of code is also working, right? And so we found that this practice of very well testing plus documenting anytime any library in the system makes a breaking change, plus bringing AI agents in, is one circle that has made this reasonable. But yeah, I do have to spend a good 3-4 hours each of my mornings, making sure to do I get 100 things that come up on GitHub that I have to always worry about with the maintenance burden, right? That there is a thing where other people have to help out with this over time. And the other thing that you see is that we have really, really, really big tests. I mean, if you go to ordinary DiffyQ, right, you'll see that I think that the full test suite takes about 100 hours to run if you're to run it in serial. So we have a lot of parallelization inside of our testing system. Well, I guess this was yeah. Well, Julia 1.12 just came out, so there's some regressions. But you'll see, there's tons and tons of, like that was an 11-minute test, 15-minute test, 31-minute test, and there's tons and tons and tons of these, and for different solver sets and whatnot. This is just one of the 100 libraries. So there's hundreds and hundreds of hours of CI testing. That's really the backbone of making sure a lot of this stays together as well. But yeah, you are taking on more maintenance burden, you are taking on more CI burden, but you gain a lot in terms of the development velocity if you're willing to take on that burden for the students. But yeah, it also means that when you're there with a student, you should be looking at every single piece of code, because when they go away, you need to maintain their code as well. So great question.
I think we have time for one more question. Yeah, so Angie, please go ahead.
Hi, my name is Mazai, and I'm wondering, was there someone else?
No, it's okay. Please
I'll
go
go
ahead.
for it.
Okay. I was wondering about the future of a language like Julia when you have Python, which has a larger ecosystem, as you have pointed out, are now changing in ways that make it similar in terms of speed, for example, by incorporating JIT compiling. What would you make of that? That these other more established or older languages are now changing in ways that are evolving in ways that speeds up a lot of what previously took a whole lot of time.
Yeah, great question. I think that one thing is that, even if you make these changes, it takes a very, very, very long time for these to propagate through all the libraries and to be able to be used. And so one thing is, like Python had a version that came out that said global interpreter lock is fixed, right? Well, it's turned off by default because most libraries can't support it. And this is something that's going to take another 5-6 years to even work out. And then they'll have a slow threading model, right? And then they have to actually change a lot of things from there, right? So I think there's a little bit there's a bit that's overblown in terms of like what's changing in some of these languages, and it really is because the language semantics actually matter for what you're able to do here, right? I think Jan Vitek has a very good talk about building a JIT compiler for R, where effectively what his talk is about is why they failed to actually build a JIT compiler for R, and it's because the semantics of R as a language are not amenable to be able to build a good JIT compiler, right? One way to be able to show this, for example, for Python is that, Python has a semantics where you can build a struct or an object that has two fields in it, right? And then somewhere in someone else's code, in someone else's package, they can actually add a third field to your struct or to your object, right? So if you're going to make your JIT compiler work, right, your JIT compiler has to say, well, this is something that takes through two float 64. So like, well, you can't actually make that assumption because once you add this other package, now it's something that can take three float 64s, right? And this can happen actually anywhere in code, right? And so this is a semantic where you say, if I want to actually build a good optimizing compiler, I cannot allow that semantic, right? And there's lots of these semantics that exist within the languages like Python, right? So for example, you can have a square root of a floating point number can either give you a floating point number or a complex number. So your JIT compiler has to take into account the boxing and everything that can happen with that, right? So just putting a JIT compiler on something does not actually make it faster, right? You have to actually have code semantics that then are amenable to optimizations and amenable to this. Jan Vitek's talk is a very good talk about all this, and this is actually why you kind of see a floor, right? Python code only gets 7 times faster. Like Python code is like 500 times slower than like C, right? And it gets 7 times faster with the JIT compiler. The rest of it is things that have not been able to be handled after the billions of Google dollars. And I don't think it's something where you just say if we make that trillions of dollars, it goes away, because it's actually fundamental to the language semantics that unless you change the language, a compiler cannot optimize some of these semantics, right? And so then you have the question of, okay, well, what if they do that breaking change where they change this per piece, they make it so that way square root of always gives you a real number or an error, and what if they change it so that way you cannot have your structs be different and everything? If you make a breaking change, all these different breaking changes, A, I don't think Python will do that because it will happen in Python 2 to 3, but B, the language that is all this changes about being a dynamic programming language with those restrictions is effectively the design of Julia, right? And so they might go towards Julia, but I think unless they're really willing to make a lot of breaks, it can't happen. And so I recommend going into a lot of the details about how the JIT compilers work to really kind of see and understand where that difference comes from. So it's not just about being a JIT compiler, it also has to deal with language semantics.
Thank you very much. So let's thank the speaker one more time with a virtual round of applause. We will now have a break until the next hour. So 10 p.m. if you're in Finland, something else o'clock if you're somewhere else. And after the break, we will continue with 2 invited talks.
Yeah, thanks for having me.
Yeah, thank you.